Okay, section 12.2 is on probability. So it says, suppose you have the following experiments. List the sample space. What a sample space is the set of all possible outcomes in a certain experiment. So an experiment could be rolling a die, flipping a coin, rolling a die and flipping a coin, lots of different things. Okay, so if I have a sample space, what I typically will do is I write S equals, and then I do your favorite mathematical symbol, the brace, and you list all the outcomes in between the braces. So for example, so flipping a coin would be heads and tails. Okay, and rolling a die would be the outcomes 1, 2, 3, 4, 5, and 6. And then something like counting the number of the stars in the sky would be debatable. 0, 1, 2, 3, and dot, dot, dot. So you could have an infinite sample space as well. An event would be any set of outcomes in that sample space. So if you had 2, 4, and 6, that would be an event rolling an even number. The probability of an event is always a number between 0 and 1. We would never say the probability is 50. You might hear people say 50%, but really the better way of saying it is the probability is 0.5 of this happening, okay? So it's always a number between 0 and 1. So if you guys on your homework write the probability is 1.2, I know immediately that you're wrong because it can't be 1.2. So it says, suppose that a box contains 50 candies. Okay, 20 are strawberry, 15 are grape, 10 are lemon, and 5 are orange. An experiment consists of drawing one candy from the box and observing its flavor. So your sample space would be strawberry, grape, lemon, and orange. And you can abbreviate if you would like. So it says, what is the probability for each flavor? So let's say I talk about the probability of strawberry. Well, there were 20 strawberries out of a total of 50 candies. So I have 2/5, or you might write that as 0.4. I usually prefer the fraction form. The probability of grape. There are 15 grape out of 50. If I divide by 5, I get 3/10, or you could write 0.3. The probability of lemon. The probability of lemon would be 10 out of 50, which is 1/5, or you could write 0.2. And the probability of orange would be 5 out of 50, which is 1/10, or 0.1. And it says verify that the sum of the probabilities is 1. And in this case, it is, right? I have 0.4 plus 0.3 plus 0.2 plus 0.1. I end up getting 1. Okay? And that actually will always happen. The probabilities of every single outcome in the sample space should always add up to be 1, because that's 100% of the outcomes. So it says, what is the probability that a strawberry or orange candy will be drawn? And when you do this, you can do the probability of strawberry or orange, and you could look back at your original, and you could say, oh, well, there's 20 strawberry and there's 5 orange, so it's 25 out of 50, which is 1/2. Or you could actually even take the probability of strawberry, which was 0.4, the probability of orange, which is 0.1, and you could add them together. Okay, these events are what we call mutually exclusive, so we're allowed to do that. Okay, but you're not always allowed to do that, so I want to caution against doing that all of the time. For instance, if I talked about the probability of someone having a sister and the probability of someone having a brother, those could be certain numbers, but maybe the probability that someone has a sister or a brother wouldn't necessarily be adding those together. Maybe someone has both. Maybe someone has a sister and a brother, and they've been counted in both of those probabilities already. So it's a little bit tricky when you talk about that. Okay, the complement of an event is the opposite of an event. And this just helps when we are counting sometimes. Sometimes it's easier to count the opposite than actually counting how many of something else we have. So we write complement as a complement or a bar. Okay, so it says a single card is chosen from a standard deck of 52 playing cards. What is the probability that it is not a king? So we would do not a king like that. Well, it might be most useful to find the probability that it is a king first. The probability that it is a king would be, there are 4 kings out of the 52, which is 1 out of 13 if you reduce. So the probability that it is not a king bar, is going to be the rest of the probability. So 1 minus 1/13, which ends up being 12 out of 13. Okay, so if I had counted up all the things that were not a king, I would have had 52 minus 4, I would have had 48 outcomes. 48 out of 52 does reduce to be 12 out of 13, so you can do it either way. So then we talk about face cards. So the probability of getting a face card Now, face cards are the ones with faces, right? Jacks, queens, kings. We do not include aces. A lot of people think we can include aces, but we don't. So a face card is going to be 12 out of 52, which reduces to 3 out of 13. So the probability of not getting a face card would be the rest. It would be 1 minus 3 over 13, which is 10 out of 13. So we do the opposite. Okay, so here's an example of one where it's very useful to use the complement. Okay, in a previous lesson, we drew a huge chart that involved throwing 2 dice. So we had 1, 1, we had 1, 2, 1, 3, and we had this huge chart, and we had 36 possibilities in the whole thing. Okay, but we don't have to draw out this huge chart when we talk about 2 dice. Sometimes we can just think about the number of outcomes in our head, knowing that we've drawn this chart before. So what's the probability that you get a sum greater than or equal to 4? So in order to do this, what I want to do is find the probability that my sum is less than 4. That's the complement, right? I don't do less than or equal to, because then I would be including 4 in both of those steps. So I do just strictly less than 4. So I need to think about all the different ways I can have a dice, and I can 2 dice, and I can get less than 4. So I could get a 1 and a 1. I could do a 1 and a 2, and I could also do a 2 and a 1. Okay, so I can't do 2 and 2 because then that would be 4, and I can't do 3, 1, and 1, 3 for the same reason. So there's only 3 outcomes. Out of the total was 36 outcomes when you drew the chart. So I have 1 out of 12. So the probability that my sum is greater than or equal to 4 is the rest of the probability. So it's 1 minus 1 over 12, which ends up being 11 over 12. And if you had counted on the chart from the previous lesson, you would see that we had 33 out of the 36 that were bigger than or equal to 4. All right, whoops, I forgot to erase this one. So I'll erase really quickly. So now we're talking about odds. Okay, so if I have odds, the odds that something will occur can be expressed as the ratio of the number of ways it can succeed to the number of ways that it can fail. Okay, and casinos are known for writing things in odds. So if you guys are going to be gambling someday, which I'm sure that you will go to the casino maybe once or twice, maybe more in your life, then you probably need to be educated gamblers, okay? And when you walk into a casino, it's going to say something like, the odds of winning a game is 3 to 4. And you're going to think, wow, I have a 75% chance of winning this game. I'm going to play this game. But what that actually means is that there are 3 ways to win and 3 ways to fail. It's a number of ways to fail. So if I was playing this game 7 times, I would win 3 times and I would lose 4 times. So my probability is not 3 out of 4. Oops. My probability is 3 out of 7. Okay. So it's very, very different. So you want to do the total on the bottom for probability. So why would casinos use this? Because frankly, it looks better, right? When I see 3 to 4, I'm like, ooh, I have a 75% chance of winning. That's what a lot of uneducated consumers will say, right? They'll say, oh, 75% chance of winning. I'm going to play this game a whole bunch. But your probability is actually less than half. It's 3 out of 7, which it always is with gambling games, right? It's the casino wants to win, right? So the next one says, according to the U.S. National Center for Health Statistics, the chances of a male born in 1990 living to at least 65 years of age are about 3 in 4, so 3 out of 4. For a female, the chances are about 17 out of 20. So what are the odds? So it's kind of morbid, but in this case, 3 ways to win, 1 way to lose is how we consider it, 3 to 1. And for a female, 17 ways to win, 3 ways to lose, right? So what I'm doing to get that 3 is I'm taking 20 minus 17. I'm taking the total and I'm subtracting out the number of ways to win. So odds and probability are very, very different. You need to consider that. Okay? Does anybody know why those are different? The reason that our probability of living past 65 is not, like a lot of people will think it's because of heart attacks. They think that men have more heart attacks, and that's not true. Women actually do have more heart attacks. We just don't have the same symptoms of a heart attack. Like we don't have the pain in our left arm all the time. You know, like. But men always have those classic symptoms of a heart attack. So women actually do have more heart attacks. They have more heart disease. The reason that the men die more often is because they are bigger risk takers. And risk is something we definitely study as mathematicians. So there are people called actuaries that study how often or how risky someone's life would be. And they come up with things like they work for insurance companies, or they work for life insurance companies or health insurance, and they calculate risk for a living. Okay, so the next one. So find the odds of each outcome if the computer randomly chooses a letter in the word Alabama. So the odds of getting an A would be there's 4 A's, and then there's, let's see, 7. Are there 7 letters? Yeah, so 4 to 3. So 4 ways to win, 3 ways to lose. Next one, 1 to 6, 1B, 6 other letters, and 1M, 6 other letters. Okay. The next thing we're going to talk about is independent versus dependent. So things are considered to be independent if the occurrence of one event has no effect on the probability of the other. Okay, so that was like when we talked about rolling the die and then flipping the coin. It doesn't matter that I got a 6 on the rolling the die. It has no effect on what I'm going to get when I flip that coin, right? Those are totally separate things. They have no effect on the other. That would be independent, okay? But if we have something that does have an effect on the next thing, like a raffle, if I was doing a class raffle and I was drawing someone's name out of the hat, so Audrey is my first winner, right? That means that, and I take her name out so she can't win that next prize, out, then that affects everyone else that's in the class. It affects their probability of winning that next prize, right? So that would be called a dependent event. It changes the probability for that next thing on the tree, okay? So an example, if you flip a coin 700 times, it doesn't matter what happened on the first 699 flips. You could possibly get heads for 699 flips. It's not going to happen, but you could get heads for 699 flips. It has no effect on that 700 flip. It's still a probability of 1/2. So if A and B are independent, then the probability of A and B occurring is just the probability of A times the probability of B. This is not true for dependent events, so be very careful. Don't just assume that you can't draw a tree or think about a tree. You should always be thinking back to those probability trees that we did. So for the first one, so let's draw a tree and see what happens. So we're flipping 2 coins. So my first outcome, I get heads and tails. My second outcome, I get, again, heads and tails. So my sample space is heads, 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 tails, tails, heads, tails, tails. There are 4 outcomes. Each of these probabilities does indeed have a probability of 1/4 because it's 1/2 times 1/2. So this one is 1/4, 1/4, 1/4, and 1/4 for the totals. So the probability that I get a tail on the second flip ends up being this one and this one, right? It means I could go this route or I could go this route. So it's 1/4 plus 1/4, which ends up being 1/2. And then you think, well, of course it's 1/2 because it doesn't matter what happened on that first flip. I could have gotten heads or tails. My probability of getting a tails on that second flip is still 1/2. So sadly, I have been the person where on my probability homework or probability test, I don't remember what it was, but my teacher asked me, what's the probability of getting a tail on the 4th flip? And I drew out this tree for 4 outcomes, so 4 flips, and I ended up having 16 possibilities at the end. And then I added up all the different things, and magically, what did I get? I got 8 out of 16, which made 1/2. So I've done that. I've been there where I've done something stupid and I've got too far. Okay, so don't do that. Always think, well, it doesn't matter what happens in the first flips. So same thing here. So if I'm rolling a die and then flipping a coin, then I'm going to have, for the die, I'm going to have 1, 2, 3, 4, 5, 6. And then flipping a coin, I'm going to have heads and tails, heads and tails, heads and tails. And you can fill out all of the different probabilities, right? For all of the numbers, it was 1 out of 6. For all of the heads and tails, it was 1/2. But I'm finding the probability of getting a 6 and then an H. So the probability of 6 was 1/6. The probability of heads was 1/2. So it ended up being the same as the probability of 6 times the probability of H because they are independent events. It doesn't matter what happened when I flipped the coin. It has no effect on the heads or tails. So it's 1/6 times 1/2, which is just 1/12. That's why it's working the way it is, why the formula works. All right, the next one, it says, what's the probability of the probability of losing a game is 0.7. If the game is played twice, what is the probability of losing both games, winning both games, losing once, and winning once? Okay, so I'm going to have let's do winning and losing. Winning and losing. And then I'm going to have winning and losing, winning and losing. So my probability of losing is 0.7. That means my probability of winning has to be the rest, 0.3. So every time I have a win branch, it's 0.3. Every time I have a lose branch, it's 0.7. So the probability of losing both games would be 0.7 times 0.7, which is 0.49. The probability of winning both games would be 0.3 times 0.3, right, which is 3 over 10 times 3 over 10, so it's 9 over 100. So we read that as 9/100, 0.09. But then the probability of losing once and winning once means I could find lose-win, but I could also find win-lose. So I need both outcomes. So I could go this route, or I could go this route. So I'm going to have lose-win would be 0.7 times 0.3. Win-lose would be 0.3 times 0.7. So both of these I get 0.21. So I have 0.42 as my answer. I'm going to pause here. All right, so we're talking about independent versus dependent. Okay, so independent is when you have a certain event and it has no effect on the thing that happens afterwards. So like you talked about rolling a die and flipping a coin. If I roll a die, it doesn't matter what the probability was for that. My probability of flipping the coin is still 1/2. Okay? Dependent is where your probability changes. So these next examples that we have, the probability is changing after each outcome. So after each thing happens. So it says, number 1, a card is chosen at random from a standard deck of 52 playing cards. Without replacing it, so we're not putting it back, a second card is chosen. What is the probability that the first card chosen is a queen and the second card chosen is a jack? So what we're envisioning is a giant tree diagram, okay? So imagine we have this tree. The first route that we're going to go is going to go towards a queen. The second one's going to go towards a jack. Well, the probability of getting a queen was 4 out of 52. But then once we have that, the probability of getting a jack changes, right? What's it going to be? It's 4 out of 51, exactly. Because now there's only 51 cards because we've now selected that first queen. Does that make sense? So the probability of getting a queen and then a jack is this. So you can reduce it out, like you can reduce 4 and 52 and you would get 1 over 13. But I don't think it reduces anymore. So 4 over whatever 13 times 51 is. So we get 4 over 663 as our answer.
Mm-hmm. On the test, like, are you going to put probabilities on the calculator portion?
Yeah, like that kind of stuff would be a calculator one. Yeah. Okay, so Mr. Crawley needs 2 students to help him with a physics demonstration for his class of 10 girls and 8 boys. He randomly chooses one student who comes to the front of the room. He then chooses a second student from those still seated. What is the probability that both students are girls? So the probability of getting 2 girls. Okay, so of the 10 girls, so there's 10 girls and there's 18 total, right? So the probability for getting that first girl was 10 out of 18. All right, once he selects the girl, what's his probability of choosing a girl in the next one? Yes. Exactly, so 9 out of 17. Okay, so we're going to have 10 out of 18, so it reduces to 5 over 9. It looks like the 9s would reduce, so we get 5 over 17 as our answer. All right, Valerie has a basket of thread that she uses for craft projects. The basket contains 6 spools of white, 4 of black, 3 of red, 2 of gray, 2 of yellow, and 1 of green. So if she reaches into the basket and she selects 3 spools of thread at random with no replacement, what is the probability that she will first select a red spool, then a white spool, and then another white spool? Okay, so we're saying the probability of getting a red, white, white. So again, envision that giant tree. Okay, for the red, what's the probability of drawing the red? 3 out of what? 18. So if you count them all up, it's 18. All right, once you choose the red, you now only have 17 spools of thread. So we're going to have times, and on the bottom we're going to have 17. So how many white ones do we have?
6 out of 17.
Uh-huh. And then for the next one?
5 out of 16.
Exactly. Now we have 1 less white, so now it's 5 out of the 16. And you can reduce I'm just going to let my calculator do it. So I'm going to do 3 times 6 times 5. So I'll have 90 over 18 times 17 times 16. So 4896. So when I do 90 divided by that, remember you can always do math 1 to change it to a fraction. So I get 5 out of 272. Okay, so this is definitely, it's pretty easy. You're thinking of the tree. It's related to the tree diagram, but probability gets a lot harder. So when I was in probability classes in college, the types of questions they would ask would be crazy. They would be like, okay, we have these 18 spools of thread that you have, and now she's reaching into the basket and she's grabbing 3 at a time. Okay, if you're grabbing 3 at a time, that's a combination problem. It's like the ice cream problems we were talking about, Cold Stone, right? And then maybe she's going in and she's grabbing 5 spools of thread next, right? That's going to be a tough problem. So these definitely get a lot harder. These are just the basics of probability. Okay, so expected value. So it says the expected value is the average value of all the outcomes. You find the expected value by multiplying each outcome by its probability and then adding all of them together. And expected values are really useful in real life. So let me give you an example. So I don't know how many people there are in here. So 2, 4, 6, 8, 10, 12, 14, 16, there's 18 people here today. Okay, so let's say I'm having a raffle, and I'm like, okay, everybody's going to pay me $1 to be in this raffle, all 18 of you. And the grand prize is $2. Would you play?
Nope.
No, you wouldn't play that, right? Your probability of winning is 1 out of 18. You're not going to play for this raffle of winning $2. That doesn't make it worth it, right? But what if I was like, oh, I have $500. Who wants to play this? Will you give me $1? All of you would be like, yep, I'll give you $1. I have a chance of winning this $500. Does that make sense? Okay, so that's what expected value is. Expected value is kind of like when the winnings kind of outweigh the probability. You know what I'm saying? So we can find this number. We want to find for the expected value to be positive, as we say. So let me give you a couple of examples. So this first one says, a grab bag contains 12 packages worth $6 each, 15 packages worth $3.50 each, and 25 packages worth 50 cents each. So you're only selling these like 52 packages. Someone's not going to come along after you're out of the packages and be like, I'll give you $1 for nothing, right? That's not going to happen. So we're selling these 52. So your probability of winning the $6 one is 12 out of 52. There's 52 total packages. All right, and the amount that I'm going to win is $6 for that. So I'm taking the probability and I'm multiplying by the amount that you would win. All right, and then plus, I'm going to have 15 packages out of the 52 that are $3.50. And I'm going to have 25 packages out of the 52 that are 50 cents. Oops, 50 cents. All right, this is what I call my expected winnings. It's not quite my expected value, and I'll explain what we need to do to get the expected value. So in my expected winnings, I'm going to do 12 over 52. I'm going to multiply by 6. I'm going to do 15 over 52. I'm going to multiply by $3.50. And I'm going to do 25 out of 52. And I'm going to multiply by 0.5. So when I do that, I get $2.63. Okay, but what number have I not used in my original problem? I haven't used something. 1.5, right, $1.50, right? That's how much it cost me to pay, or cost me to buy this ticket, right? Or to buy the, not ticket, but the grab bag. So that's where the expected value comes in. So expected value ends up being your expected winnings minus the amount you paid. So in this case, my expected winnings was $2.63, but I paid $1.50. So I'm expected to make a profit, right, of around $1.13. So would you pay? Like, would you buy it? Yeah, because you're expected to make a profit, right? If your expected value ends up being negative, you don't want to play the game. Okay? You want to end up making money. So Mr. Morrison does this a little bit differently when he teaches AP Stats. So if you guys go into AP Stats, I want to show you what most probability teachers will do when they do expected value. Instead of doing what I did and doing the expected winnings, what you do is if you say, oh, the grab bag's worth $6, but you paid $1.50 for it, how much are you expected to gain? $4.50. Does this make sense? So most probability teachers will do this all at once, and instead of putting $6 here, they'll put $4.50 gained. Okay, and then this would be, you know, $2 gained. You're subtracting out the $1.50. And then this would be, if I was only making 50 cents, but I paid $1.50, that would be -1. So you could also do it that way. You could put those numbers in, and then you wouldn't have to subtract out the dollar. Personally, I think it's easier to do the expected winnings, right? Isn't that easier? All right, Katie?
So you're going to subtract it from all of the numbers?
Yeah, you would subtract it from all of them, yeah.
Yeah.
Yeah, I think it's easier just to do it at the very end, because you don't have to remember to subtract from every single one. And what if you make a mistake because you're subtracting and so on? Okay, so for the next one. So it says the table shows the probability distribution of the payoff on a $1 scratch-off lottery ticket. So each of these tickets, like the types of tickets you buy, their distributions are different. Like one ticket might be better than another, but this is a certain ticket, okay? And you can find this, I think, usually on the back, like it will tell you information about it. So anyway, so the payoff on a $1 scratch-off lottery ticket, you win $0 91% of the time, you win $5 6% of the time, and so on, okay? So what we're going to do is we're going to do our expected winnings again. And we're taking our probability times our payoff. So I have 0 times 0.91176, which is still just 0. And then I have 5 times 0.06. And I have 10 times 0.02. And it's going to take me a while to write this down. So I'm going to do ... plus 1,000 times 0.00004. So I'm going to find all of those. I'm taking each number multiplied by the number next to it, added to each number, multiplied by the number next to it, all the way down the table. Okay? And when you do this, oh gosh, I can't remember what you get. I think you get 0.78. Okay? Yeah, I'm pretty sure it's 0.78. So you can go through, you can do all of that on your calculator, you get 0.78. So what is your expected value then? Yeah, it's 0.78 minus 1. So it would be how much money? Negative 22 cents. So would you play this game? No, you would not. Does that make sense? Like you only want to play things where you have an expected value that's bigger than 0. You don't want to play things where it's less than 0 because that's meaning that you're most likely going to lose money when you play the game. It's kind of like the average amount that you're losing. Okay, so you don't want to play the game. Okay? The very last question. I think that is the very last question in this, so we're good. Yes.
So there are problems like these.
Not like these ones.